All right, we are in part 3 of this chapter, which is about gas stoichiometry. You'll notice the section number for gas stoichiometry actually comes from a later chapter in your book. The rest of this has been chapter 9. This is found in chapter 13 because it's in the chapter with gases. If you remember when we did calculations with gases, we had certain variables. We had some P's, V's, and T's, and then we had one more variable that we introduced to represent moles, and that was the lowercase n. You can kind of remember it like number of moles, so the n is like number. In this chapter, or when we saw the ideal gas law before, it looked like this. PV equals nRT. First of all, I want to point out that the math you're doing in each of these cases is multiplication. So P times V equals N times R times T. What we're doing then is let's go ahead and start by writing this equation in your notes, and let's label what each of the variables was. So P stood for pressure. Remember, pressure can be measured in various units. We're going to go with pressure measured in ATM. V stood for volume. Volume, again, can be measured in different units, but it has to be measured here in liters. N stood for number of moles. Obviously, it's moles, so it's measured in MOL. I'm going to jump over here to T. T stood for temperature. Temperature has to be measured in Kelvin to use your PV equals nRT equation. And then finally, we had R. I'm making R a different color because R is a constant. Its value was 0.0821 liters times atmospheres over Kelvin times moles. The units look really weird, but you actually don't really have to do anything with the units. You just use the value for it. As an aside note, I think a couple classes, instead of using pressure in ATM, we're actually using pressure in kilopascals, kPa. If you were using pressure in kilopascals, you had a different number for R, which was 8.31 liters times kilopascals over Kelvin moles. For you guys, I'm going to trust that you remember to use that one, but the rest of us are going to focus on the 0.0821 value because that's the more commonly used one, is the one with the ATM. So I'm actually erasing that value because I don't want most of us to write it down. That was just an aside if you used kilopascals before. We'll focus on ATM. So what we're going to do here is we're going to use the ideal gas law, which is the fancy name for this PV equals nRT, or as you might have heard it called before, PIVNERT. So this PIVNERT, or ideal gas law equation, can be used together with the mole map. So we're kind of combining what we know about gases and moles. For these problems, what you'll find is that they have two parts. They're going to have a PV equals nRT calculation, and they're going to have a stoichiometry calculation. It says on your paper that this can happen in any order, meaning sometimes you have to do the gas law part first and then the stoichiometry. Other times you might have to do the stoichiometry first and then go back and do the PV equals nRT. I'll explain what I mean, and you can also follow along on your mole map. On your mole map, notice that we had sections for pressure, volume, and temperature on either side of our mole map. And we had reviewed how we used PV equals nRT, the ideal gas law, to convert between those different variables. So we can convert to and from PV equals nRT just as well as we could convert to mass or to molecules or to moles or any other unit on here. So let's try practice problem 5 together. This problem says calculate the volume. So V is what I'm trying to find. Specifically, this is a volume of carbon dioxide, CO2. So volume of carbon dioxide is what I'm trying to find that is produced from the decomposition of 125 grams of calcium carbonate at STP. And I'm given a chemical equation here. The calcium carbonate is the CaCO3. If you struggled with naming, an easy way would just be to look at the equation you see here, and out of this equation, pick out which of these formulas has calcium and has carbon to make the carbonate in it. And that would be the first one. Okay, so what I have here is I have a mass of calcium carbonate, which would be like my chemical A. That's what they give me to start with. So if I look on my mole map, I can see that they're giving me grams of a chemical A to start with. So this is the box I'm beginning in on the mole map. Checking back in with the problem, I see that what they asked me to find was the volume of a different chemical, carbon dioxide. So that would be my chemical B. So they're asking me to find a volume of a chemical B. On my mole map, that means they're asking me to end in this box over here, the pressure, volume, or temperature of a gas B. Here is specifically the volume that we want to find. So I can see that I'm going to be going from the top left corner of my mole map to the middle right of my mole map. So let's focus on the steps. The first step is I'm going to use the molar mass of my chemical A to change grams of A into moles of A. So let's go to our problem and do that. I'll start by writing 125 grams of CaCO3 times in a line. I started with grams of calcium carbonate on the top, so I'm putting it on the bottom here. And moles of calcium carbonate is what I'm trying to do. So my first step is always to change whatever I'm given into moles. The mole gets a 1 with it, and because I'm trying to find grams, this means I need a molar mass of CaCO3. So adding that up, calcium is 40.08, carbon is 12.01, and I have 3 oxygens, so that would be 3 times 16.00. This gives me a total molar mass of 100.09. So that 100.09 goes for the molar mass of calcium carbonate in my first step. Let's do some unit cancellation. I started with grams of CaCO3, and now I have grams of CaCO3 in the denominator. That cancels out because this one was on top, this one was on bottom. Boom. For my next step then, let's figure out where I'm at on that mole map. I was right here at moles of my chemical A, and now they're asking me to go the next step. My next step is going to be to make a mole ratio, which uses the coefficients to find the moles of the chemical B. So I'm going to use coefficients from my balanced equation. So right here, I'll put another times in a line. The unit I had on the top now goes on the bottom, moles of calcium carbonate. The unit I'm trying to find, which is moles of my chemical B. Here my chemical B was carbon dioxide, goes in the numerator. Now to fill in a mole ratio, where do I have to look? I have to look in my balanced chemical equation. Well, right here I see that the calcium carbonate had no number in front of it. That's like a 1. The carbon dioxide also had a 1 in front of it. This is a 1-to-1 mole ratio. Even though I'm multiplying and dividing by 1, I still need to show that step because it's about changing the units, and we have to be careful with our labels. So let me go back and take a look at my mole map now. I got to moles of B right here. Now they're asking me to find the volume of my gas. And what I actually find here is I got a little carried away in my problem. I'm not doing another times in a line. This is where I need to use PV equals nRT. So in my problem, let me get rid of this line I had here. Let's go ahead and get an answer for this, and then we will use PV equals nRT. So the answer I got for this step was 1.25 grams, nope, not grams, 1.25 moles of CO2, carbon dioxide. I can't box my answer though because I'm not quite done yet. This was the first half of my problem doing stoichiometry. The second half of my problem is to use the ideal gas law, PV equals nRT. So to label, I started by doing a stoich, which is my nickname for stoichiometry. And now I'm going to have to do a PV equals nRT equation. Let's look at the values we know. Well, right here I had a value of moles. That's going to be my N value. In the problem, I don't actually see any more numbers, and that's because they're being kind of tricky here. In this problem, I said we were at STP. Let's review what that stands for. STP represents standard temperature and pressure. This is a set of conditions that scientists agreed on as kind of their reference point, standard temperature and pressure. Because I'm at STP, I know a few values. The standard temperature is 0 degrees Celsius, which if I change it into Kelvin by adding 273, I get 273 Kelvin. The standard pressure is exactly 1 atm of pressure. Or if you were using kilopascals, it would be 101.3. So what this means is I have a value for T, I have a value for P, and I have a value for N. Because I have values for those three variables, the P, the N, and the T, I also know a value for R, because remember R is a constant. R always has the value 0.0821 liters times atmospheres over Kelvin moles. What I can do now is plug all those numbers I know into the equation and solve for V. So let's do that. I like to start by writing my equations so I know what I'm working with. P times V equals N times R times T. Those are all multiplication. The pressure here is exactly 1 atm. The volume is what I don't know, so I'll leave that as a variable. My number of moles is 1.25. That was the answer I got from the first part of the problem, remember? R is a constant. That's 0.0821 liters times atmospheres over Kelvin times moles. You don't have to do anything with those units. They're just there to make everybody else cancel out. The temperature, because I'm at STP, is actually 273 Kelvin. And now I'm ready to solve and do some algebra to get V by itself. Right now, V is being multiplied by a number, so in order to isolate the V, I need to divide both sides by that same number. So dividing both sides by 1 atm, that gets me the V alone on the left-hand side of this equation. And now I punch a bunch of numbers in my calculator. 1.25 times 0.0821 times 273 divided by 1.00. The answer I get here is 28.0166 ... Let's think about our significant figures here. The moles that we had from before had 3 significant figures in it. My pressure is an exact number at STP. My temperature had 3 significant figures. My R value had 3 significant figures. Do you notice a pattern here? I'm going to go with 3 sig figs. In this case, I would write that as 28.0. The units that I get for this, notice right here, the moles canceled, the Kelvin canceled, and the atm canceled. All I had left was liters. So my answer here is 28.0 liters. I can't just write 28 without the 0 because that would only have 2 sig figs and I need 3. Okay, now it's time for you to try practice problem number 6. Go ahead and pause the video here and try to set up and calculate practice problem number 6 on your own. So if you did practice problem 6 and you got an answer of 5.6 or 5.8 grams of water, somewhere right around there, you did it correctly and you can skip the little tutorial on that one. Otherwise, go ahead and stop this video and you'll find a separate video that explains practice problem 6.